In this presentation, we will show you the design process we went through to arrive at our final design, how we performed at FEDD Day, and what we learned as a result of our experience.
The very first step of the engineering design cycle is to identify the problem or challenge. The main challenge of the project was to design a canoe made of concrete that will effectively float on water. Before actually building the canoe, the criteria and potential constraints must be identified. The dimension of the boat needed to meet a specific set of standards. The length of the canoe can be no more than 18 inches. The width of the canoe must be within 1/3 the length of the canoe. Lastly, the depth of the canoe in water cannot be more than the width of the canoe minus 1 inch. Along with meeting the specified dimensions, the concrete of the canoe must be reinforced, meaning that the concrete should consist of liquid, cement, aggregate, and reinforcing agent like chicken wire. The final model, both of reinforcements and aggregate used in the concrete mixture, should not be visible. As far as the canoe structure goes, a V-shaped hull design must be developed that will maximize the cargo capacity of the canoe.
We brainstormed a few possible ways to go about building our canoe. Initially, we thought that we could create a solid block of concrete, then use a Dremel tool to shape and hollow the design into that of a canoe. Another option that we came up with was to create a skeleton of chicken wire, then paste a layer of concrete around the wire. Finally, we thought that we could create a hull out of a block of foam, then use the foam hull as reinforcement for a layer of concrete. A series of quick sketches were drawn up to illustrate these multiple ideas. We also explored ideas regarding what cement, aggregate, and support mixture to use. We considered the use of hydraulic cement, regular Portland cement, or air-entrained cement with our design.
None of us had much of an idea what makes a canoe different from other kinds of boats, or what angle constituted a V-bottom hull. We did, however, have a concept of what we'd like it to look like for the maximum buoyancy. We made a sketch of the cross-section of our canoe, with the maximum allowances marked for reference. Using this sketch as a guide, we began our research.
In order to accurately evaluate our ideas, we made a list of pros and cons. This allowed us to come to solid conclusions and proceed with confidence in our design.
While developing the shape of our concrete canoe, we had to keep in mind that the hull could not be a flat bottom and must be V-shaped. This, along with other dimensional constraints, made it important to create a mold of our canoe to lay the concrete and reinforcements on. We decided to use styrofoam as the mold, believing that this would make a sturdy and easily manipulated form. Once this was formed, we covered the mold with chicken wire, since this could create a strong structure without adding too much weight. After this, we created a concrete mixture of hydraulic cement with sand and styrofoam as our aggregates. This concrete that we had created was resistant to leaks as well as lighter than usual.
In order to make the canoe float, we needed to find the optimal dimensions and hull angle. We chose to make the canoe 18 inches long, 6 inches wide, and 5 inches tall, the max dimensions allowed, so the volume would be maximized as well as the buoyancy. From our research, we found that the best angle for the hull would be 10 degrees from the ground. This angle helped provide the maximum volume on the inside while still being considered a V-shape.
With our newfound knowledge of canoes and their several caveats, we headed back to the drawing board, using Crayoparometric 2.0 to develop a more detailed technical cross-sectional drawing. We extruded and revolved this drawing to create a full-form 3D model of the canoe. Satisfied with the way this model looked, we decided to move on to the build process.
Initially, we tested out the concrete and foam to see how well they bonded together, as well as the buoyancy. We then constructed a full-size prototype consisting of our styrofoam hull and reinforced concrete.
After completing the prototype, we then had to make alterations in order to meet the design constraints. The addition of extra concrete put us slightly above the height requirement, so we trimmed a section off of the top rim. We also discovered that we could not keep the foam hull within the body of our canoe. We cracked open the inside walls, scooped out the foam with a spoon, and then recoated the entire body with another thin layer of concrete. After allowing the new layer of concrete to set and dry, we then sanded the body to create a uniform, smooth surface.
When we tested our canoe on FEDD Day, it held about 4.3 kilograms, which is about 10 pounds. We held more weight than any other concrete canoe in this year's FEDD competition.
back and you'll hear a tale of a fateful trip that started from this tropic point aboard this tiny ship.
We learned that a project that seems simple in concept can actually turn out to be very complex. In our case, finding a suitable design and figuring out the proper type and mixture of concrete turned out to be extremely challenging. Constructing the physical model took more time and effort than we initially planned, and we ended up having to alter our initial prototype. We also learned about the importance of teamwork and how a project can run smoothly if everyone does their fair share of work.